Well, hello. My name is Randy Walden with Armstrong International, and today we want to take a few minutes to clarify some issues that are common problems in heat exchanger drainage throughout a multiple of different industries. We're lucky enough today to have a working model of a glass heat exchanger that most process engineers don't actually get to see what happens inside the piping or inside the heat exchange equipment. So what we're going to do is kind of run you through the system that we have, and then we'll go through some different variables that take place in the process loop that will hopefully allow you to troubleshoot systems better, evaluate potential issues that they have, and come up with intelligent solutions to solve their problems. To start off with, to let you know what we have, is we have a glass shell and tube heat exchanger. In this case, we have a process fluid coming in this case which is water, flowing through the tubes. We have the process in the tubes and the steam in the shell. The water coming in on the right-hand side, as you can see, is a variable flow. We have the ability to vary that flow, just like you would see a different process demand on any kind of heat exchanger. The beauty about the lesson we're going to learn today is that heat exchange equipment, the variables we're going to talk about, are common whether you're heating air or whether you're heating glycol or ethylene, okay? The variables that we're going to point out are always areas that can change within the system, and when those changes take place, they have different effects on both the equipment itself and the downstream equipment, like our traps, like our pumps, and the other products that we make. We are feeding the shell side of this heat exchanger with saturated steam. We're coming off of a 50-pound header, dropping down, coming through one of our control valves, where the control valve has the ability to modulate the steam flow based on the process demand. We have inherently built in a control panel over here that allows us to stroke this valve and simulate different process variables within the loop. We come up, we feed the top side of the exchanger over here on the right-hand side, and that's where the steam comes into the top side of the shell. We then, of course, have the condensate outlet coming right out the bottom. In the case that we have right now, the scenario that we're simulating is strictly going from the exchanger over to some type of steam trap, whether that be an F&T trap that we have at the top, a thermostatic trap that we have in the middle, the IB trap, or at the bottom, an orifice type trap. We have the ability in this system to open another motorized valve that allows us to feed our pumping trap system. Now that we've kind of laid out what our piping arrangement is, let's talk about some of the problems that we commonly incur with exchangers. One is variable flow rates. As we look at right now what the condensing rate is, you can notice that as you see the liquid going through the tubes, you'll see that there's a continual amount of bubbles that travel through those tubes. That's entrained air in the actual process flow, okay? One reason it's so important to get it out over here with our ball float air vent on the process side, the 11AV. What we're going to do now is I'm basically going to increase a little bit of pressure on the bundle. You'll note that right now the gauge is showing an outlet pressure on the heat exchanger of 5 pounds. Let me take a minute to emphasize the importance of where pressures are taken as we try to troubleshoot these systems. the inlet pressure that's fed to a heat exchanger is normally always dependent on what the process flow is telling this control valve that it needs. However, what affects all of this equipment down here, whether it's steam traps, whether it's pumping traps, is the actual outlet pressure of the exchanger. The outlet pressure varies based on how much process flow we're trying to heat, how much surface area we have to achieve that heat transfer, and also by how much back pressure we have here. That affects the total throughput of any of this equipment. So we have to understand what those variables are to make a proper determination of why we have issues or have potential issues. Okay? As we go through the traps, we see that we have 5 pounds on the inlet, and right now we're going to 0 psig on the outlet side. That's because we're going to drain. As we continually try to help our customers optimize these systems, we know that hot condensate is worth a lot of money. So typically, we always try to recommend capturing this condensate. But when we start capturing condensate, that also creates other issues for us, okay? Like back pressure. In low pressure systems, back pressure is one of the most common problems that we incur when we try to evacuate condensate from a steam space. What we're going to do now is I'm going to slowly valve out this atmospheric valve. And we're going to slowly, as you can see, start to build up level in the condensate return piping. As you see the condensate being drained through the trap, the differential initially on this trap was 5 pounds. We had 5 pounds on the outlet of the heater coming to the trap. We had 0 psig at the drain. Right now, what we've just done by valving in the condensate header is we're slowly inducing back pressure on the trap. We're inducing the back pressure by allowing the liquid head to generate. Look at the level now. The level is almost to the top, but remember, 1 psi for every 2 feet. There's a foot, there's a foot, there's a foot, there's a foot. So we're slowly cutting back on the differential across this trap by generating that amount of liquid head. The other thing we always have to remember is not only do we have liquid head in the vertical rise, but we also have the pressure that exists in the condensate header itself that we run, usually in an overhead return scenario. What we want to do now is I want to slowly actuate a valve that will allow us to observe our pumping trap system and how we can optimize those exchangers by allowing them to run in the lowest possible pressure. Again, as steam experts, we all understand that the latent heat content in lower pressure steam gives us a lot more heat value per pound than does the higher pressure steam. So what it makes sense for us to do is to run those exchangers at the lowest possible pressure to optimize their performance. Okay, what we wanted to do was continue and show you what we've done to actually equalize our pumping system into the outlet pressure of an exchanger. What we're wanting to show is graphically show you that our ability to continually drain an exchanger, regardless of its condensing rate, regardless of its outlet pressure, regardless of all of those variables that we just discussed that can cause issues. If we engineer the downstream side of these exchangers correctly, we can ensure that we never corrode the tube bundles because we always keep the surface area dry on the exchanger. That's of very, very large value to all of our customers, regardless of the heat transfer setup, whether it's an air coil or a heat exchanger or a reboiler. Okay? What we've done was we actuated the valve on the outlet of the exchanger that allows us to free drain down into a closed loop pump trap scenario. We realize that now we have products that incorporate both the pump and the trap together. However, for us to graphically and visually allow you to see what takes place in these processes, we wanted to keep this separate so you could see what happens with the traps and how the pumps work in conjunction with the traps. Right now, you'll see the outlet pressure of the exchanger is at 5 pounds, like it has been. No different. We have 5 pounds coming in, we have 5 pounds coming around, and we have 5 pounds that should be coming right to the steam trap, okay? And remember this is critical. It's a common mistake that even some seasoned veterans make. I don't care what pressure you feed that exchanger. What matters to us is what's on the outlet of that exchanger, okay? We can see that we have a floating thermostatic trap on the downstream side of the pump. This trap is installed so that if the outlet pressure of this exchanger coming through the system exceeds the back pressure that we have trying to lift this condensate and get into the header, we would have steam flowing all the way through this if we had no steam trap. As you see now, we have about 8 feet of lift, roughly. That's about 4 pounds. Right on the outlet, we're at about 4 pounds. So you can see through the flow indicator that we have no flow through the trap into the vertical rise into the header. We're currently at what we term as a stall condition. But in essence, the technical term for it is there is lack of differential pressure. There is no pressure difference. If anything, we have more back pressure than we have inlet pressure to the trap. So regardless of how big this trap is, when there's no difference in pressure to push liquid through it, this trap will not operate correctly on this exchanger. So what we're doing is we're continually condensing in the exchanger. You'll see that we're at 4 pounds and 4 pounds. What I'm going to do now is slowly modulate the steam control valve to decrease the amount of steam flow to the exchanger, because we're going to drop this outlet pressure, and we want to demonstrate to you that this system allows the exchanger to run at either 5 pounds, 100 pounds, or in a negative pressure. Because there goes the pump. I believe it just cycled. You can see now that there is flow coming into the trap. And as we slowly start to build pressure in the pump body, you'll see the pressure slowly build here. As that happens, we will continually pump liquid into and out of the trap and into the header. And we should, as the pressure builds in the pump, we should see a flow through the vertical rise here. But note this is very important. Why is it important for the reservoir on a pumping trap? Because even though we are now in the pump out cycle of the pump, which closed the inlet check valve, we're now still condensing the same rate of liquid in the heat exchanger. We have to have an adequate reservoir to take the amount of liquid that we condense in the exchanger and allow it to gather someplace while the pump is pumping the liquid out through the steam trap. Okay? What you're going to see is the continual raise of level in the glass reservoir piping as we're trying to pump out through the trap and into the return header. Once we go through this pump out cycle, I will go ahead then and we'll go ahead and cycle the exchanger to go into vacuum and show you that it still basically allows you 100% turn down on the rates and the variables by allowing it to drain regardless of what that pressure is. Note that the steam pressure from the regulating valve going into the pump trap system that we have, it's set at about 8 pounds, okay? So we're feeding about 8 pounds into the pump. Note that now the pressure is up to about 6. Just for you guys that are selling pumps all the time, remember this. Typically, the pump case pressure will never increase over about 10 pounds of what your total back pressure is, where we're trying to pump the liquid to, because by the time the pressure in the pump case builds to that level, the liquid's already gone. It's already moving. Remember, we had no differential pressure. We were stalled. We're inducing differential pressure now by the high pressure feed into the pump, pressurizing up over the back pressure, coming in, pushing it out through the float trap and up into the header. Now, the pump out cycle is a fairly long cycle in this demo simply because we wanted you to have a glass trap. Typically, the trap downstream of your pump should be able to take the max condensate rate of the exchanger at a 1/4 pound differential so you don't bottleneck the pump out cycle of the pump. Because what happens when we bottleneck the pump out cycle? Bottom line is it takes more reservoir because I have more time for this to continue condensing and I have to have a place for more of this condensate to gather. So the function of the trap dictates what the reservoir is. The motive pressure to the pumps dictate what the trap is. So we have to take into consideration all of these things as we engineer a total condensate return solution for the exchanger.